Okay, in this video series, I continue with the beam theory um, and focus on Timoshenko beam theory. Um, as listed here, I would like to talk about the background information for Timoshenko beam theory, uh, the coordinate system and sign convention, and the map that we follow from kinematics to kinetics, and the resulting shear strain, and basically the shear stress recovery, and finally the equilibrium. Before doing that, I would like to make quick comments on previous beam theory that we had. If you recall, or if you have watched it, uh, we end up with, for the Bernoulli beam theory, we end up with a strength tensor that only one element, which is the strain in the x direction at the plane, on the plane that is normal to x, or E11, as shown here, and the rest is zero. I also mentioned that because of that, the surviving or major surviving stress is the stress due to bending, which is Ez d2 W dx2. I used a Hooke's law in a simplified version there, and one thing that you can kind of increase the extension to this. For this one, I ignored the Poisson ratio. And Poisson ratio gives you a very small stress in other direction that I would like to quickly mention it before we move to the Timoshenko P. So here I would like to say effect of Poisson ratio mu on stress tensor, basically Euler-Bernoulli beam theory. Quickly, I rewrite here that sigma ij is lambda delta ij ekk plus 2 mu eij. I mentioned the relationship for the Lame's constant, lambda and mu, and if I rewrite them here again, lambda is E mu divided by 1 plus mu, 1 minus 2 mu, and mu is G, the shear modulus of elasticity. Now, if you write these things in terms of Young modulus of elasticity and shear modulus of elasticity, we will get obviously sigma 1, which I wrote it without considering the Poisson's ratio mu. E11. If I consider a equal to 0, therefore this becomes 1, and then we get E11 for sigma 1. So basically, in that treatment, I ignored the effect of Poisson ratio, which is reasonable assumption. Another one is that the other two components, sigma 2, which is equivalent to sigma yy, also survives. Because if you put sigma 2 here, delta ij becomes 1, and then this becomes lambda ekk, which is the sum of the uh, E11, E22, E33. Only E11 survives, and E22 is 0. This is also equal to sigma 33, which is equivalent to sigma zz, because here delta 33 is 1, and again ekk is only survives because the only the if I bring it back here, the only sum of these three elements, these two are 0. For ekk, always you get this E11. And if you write these things out, is these things becomes in terms of the mu E 1 plus mu 1 minus 2 mu E11. And again, you see that for mu equal to 0, this becomes 0. So that's why we said that all the stress elements, and these are the stresses on the normal y and normal z surfaces with normal y in the y direction and z direction, and therefore we can ignore them as compared to the main stress, which is coming from the sigma xx, which is the kind of bending stress, and then we can continue with what we had. So this is a quick addition to the, and this is true for any beam theory, but for specifically for Euler Bernoulli beam theory, we get these values, but they are very small because mu is small, and so on. Okay, so let's go to the Timoshenko beam now. If we look at the treatment that we had in the Euler Bernoulli beam theory, we had a beam, say let's say cantilever. It's easier to, doesn't matter what kind of boundary condition you have, and we said that one of the assumptions that we make uh, is that perpendicular planes to the initial neutral axis of the beam will be transferred and then rotates such that, this is again Euler Bernoulli, such that it remains perpendicular to the deflected neutral axis. Now, Timoshenko relaxes this and say, okay, if you have the beam and then you get deflection, your normal, initially normal plane remains plane. So that first assumption that we had is there, but the plane which is this plane rotates without having the constraints of staying normal to the neutral axis. So this angle is no longer 90 degrees. This angle is no longer 90 degrees. So if I draw this in a kind of zoom here, let's say this is your initial neutral axis and this is the normal. So we are saying that obviously the neutral axis will rotate, I mean not rotate, be deflected by some theta. And remember that theta was absolute value, of course, dw dx. Still we have the slope here or here. This is there, but this is the new neutral axis deflected, but you don't have to have the constraint. We don't have the constraint of this plane rotates with the same angle. It will have the degree of freedom of rotating with a non-equal to dw dx angle. In other words, in Timoshenko beam, phi is not equal to dw dx, at least the absolute value. This is a very important distinction between these two. And basically what Timoshenko does compared to Euler-Bernoulli or engineering beam theory or technical beam theory, as we discussed in the previous video, is that it gives the beam more degrees of freedom. And this more degrees of freedom results, or shall we say, comes from shear deformation. So because of this, we can, as we will see, shear deformation or deflection is allowed. In Timoshenko beam. You remember that in the previous video I mentioned that the slender ratio of the beam, which is the length over a typical dimension of the cross section, becomes small and small, then you cannot ignore the shear deformation or effect of shear stress and shear strain, of course. Uh, Therefore, if you get such situation, this is what is happening. So again, this angle, which we called it phi in the previous treatment, we still call it phi with the condition that I mentioned here, and maybe box it. This is what Timoshenko says in his beam theory. Phi is not equal to dw dx. Now, what is phi then? How much is this angle? Okay, let's come here and then, and maybe I pick up another color here. So if this is theta, which I mentioned here, this is the neutral axis, old neutral axis and deflected neutral axis. So this is deflected here based on this. And if I come here and say, okay, let's get this angle here by theta. So basically this is perpendicular to the deflected neutral axis. But I get something extra. Maybe I get a blue color here. I get something extra. And that extra is due to shear gamma. If you recall, if you have shear, let's pick up a very quick element here. So if you have shear, this guy will deform to something like this due to shear, right? And this angle is gamma. This is what we are talking about. So we allow the beam um, to experience or go through deformation due to shear. That is what is happening in Timoshenko beam. So basically this phi, and therefore phi, at least in magnitude, is dw dx plus gamma. I'm talking about magnitude. We go to the sign again later. Uh, this sign convention treatment in several references is, to my opinion, is not fully treated or fully demonstrated, especially for, it is usually discussed for a specific case, but we will go back to our table that I described in the second video and use that for this one as well. So all that is it. I mean, basically, if you follow what I just said, you know the Timoshenko B theory. Okay, so and maybe I also, just to, for the sake of completeness, we say that if this is perpendicular, therefore uh, this will not be 90 degrees, right? This angle is not 90 degrees. Okay, so let's look at the displacement field now. So ui is u, again, displacement in our coordinate system, as if you recall, and w in the z direction. So this is my ux, this is my uy component, and this is my uz component. Again, w, because we mentioned that it's still in Timoshenko beam. If you recall, in the Euler-Bernoulli, we had two assumptions. Plane normal to the neutral axis remain plane. This is also the assumption that we continue to keep for Timoshenko, but we relax this one. We don't we don't not we do not force plane normal to the neutral axis remain normal. It might be at some location, but not necessarily in Timoshenko. Okay, therefore we can borrow the u 0 and this w becomes a function of x only again. And now we have to work out the u. And u is again in a universal form is z phi, as we discussed in the previous beam. So if you have this, maybe I draw it again here, but this is basically the same picture, maybe without color coding. So if this is my initial plane and this is my neutral axis deflected, and my no, no more normal, it could be any angle phi, and this point will transfer to this point. Maybe I get rid of this pi here, and this is my u. Of course, I am mapping the z translation on the top of each other. So this is u. So if this is phi, then u is z, which is the distance um, from the neutral axis to the point that we are considering. So this holds. If you recall that in Euler-Bernoulli beam theory, u was z dw dx, at least the absolute value. Now it is not dw. Phi is no more dw dx. Phi has another value which includes the shear uh, deformation or shear strain, if you like. Okay, so if this is my displacement field, then I go to the strain. And I use my formula that we had. And therefore, Eij would be a matrix of 3 by 3. So what would be E11? E11 would be E1, maybe I write it here, so would be du1 dx, which is z d phi dx. Okay. Remember that my phi definition here is the whole angle here, which combines um, the slope and the gamma. So we will substitute later. The second one, which is E12, would be du1 dy plus du2 dx. And again, I am referring to the coordinates that we have. We had x, z, and y. So this is 1, this is 2, this is 3. Okay, so u1 dy is 0 because u is not function of y. And u2 is 0, so this is 0. Now look what happens at E13. Maybe I write these u's in terms of the u and w. So this is u1, so this is u3z plus dwx. So du dz is phi because I'm differentiating this with respect to z. And dw dx is, of course, divided by 2. dw dx is dw dx because w is just function of x. So you see here, the big difference here is that this is non-zero. In Euler, this quantity, this phi, was minus dw dx, therefore this cancels out. Now, just for comparison, if you go back to if you go back here, this is what I'm talking about. This quantity becomes zero because these two angles are the same, and therefore in Euler-Bernoulli this component vanishes, but not in necessarily at every point. It is not in Timoshenko. Okay, so 2 1 is this consider 2 1 is 0 symmetric. 2 2 is 0 because everything is 0. 2 3 is 0 because 2 is 0 and 3 is not function of y. 3 1 is actually non-zero now, becomes this quantity. 3 2 is 0 symmetry. You can use symmetry here. So I put the 0 here, and 3 3 is 0 because w is just function of x, not z. So this is my Timoshenko beam strain tensor. Let's label it Timoshenko strain tensor. Okay, so far this is our kinematics. And if I come back to this, is we go to kinetics now. So from here, I can calculate the Timoshenko maybe I get a thicker pen here. Timoshenko stress tensor. Okay, so what do we have? We have sigma ij is equal to lambda delta ij ekk plus 2 mu eij. I can rewrite this in terms of the I can rewrite this in terms of sorry, my pen lost connection. I can rewrite this in terms of the more common coefficient modulus of elasticity and G and mu, and that would be E divided by E mu divided by 1 plus, we had it in the previous treatment, but I rewrite it here again. So this is shear modulus of elasticity, mu is the Poisson ratio, and E is Young modulus of elasticity. Okay, so using this formula, we can work out the stress tensor, which is again a tensor matrix, or in matrix format, it's a matrix of 9 elements. And if you work out the element, would be quite lengthy. I will write the sigma xx. Obviously, sigma xx would be non-zero because we have we have the E11 or EXX. So here it becomes um, delta ij is 1, ekk is sum of the diagonal of the e, you have non-zero, and e11 again is non-zero. So we get quite a bit for this element. Okay, maybe I substitute these things here. So if you work it out, you will get something like this. That it would be ez d phi dx 0 and g phi plus dw dx uh, again 0 0 0 for second, because p is 0 and this is symmetric again, and 0 and 0. One thing again here is that um, the effect of Poisson ratio is neglected, because if you look at yy, for example, this component, which is sigma yy, if you write the sigma yy will be the coefficient e mu, delta 2 2 is 1, ekk is sum of the diagonal again, so you get this z d phi dx. So this coefficient comes here, and 2 mu eij, which is 2 2, is 0, because e22 is 0. So you get a non-zero but very small number. So we can say that again we are assuming here that mu is almost 0, or we ignored, we neglect, maybe I should say ignored. Otherwise you will get this, and also you will get some sigma zz for the due to Poisson ratio. This is very similar to what we had for the addition that I had for the Euler-Bernoulli. This is coming from the volumetric strain element EKK, which is could be negligible, and then we take it from there. So this is for this treatment, and then we get it as here. One thing that you see here, and maybe I change color here for explaining this, this is non-zero, and this is non-zero. What is this? This is basically sigma xz. And what is this? This is sigma zx. So if I draw an element here, which is x in this direction, so we have the normal sigma xx, which is this component here. And now we have sigma xz. Now we get back our shear. And obviously on the z direction, we got our zx, which is um, on the top surface of the beam, which is normal to our z direction, but in the direction of the x. So main thing here is that this is recovered. This shear stress is recovered. Shear stress, which was absent, if you recall, absent in Euler-Bernoulli beam theory. Okay, I still need to talk about this phi more with the include the sign convention. So I will do that. But before going there, uh, I would like to point out here that uh, this is better than in terms of shear deformation, at least consideration. It is one level better than Euler-Bernoulli. But if you look here, uh, this in this function here, this quantity is not function of z. So this shear stress is not function of z. So this is constant shear stress along the, and maybe I do it here again. This is a very important conclusion from Timoshenko beam theory, that yes, we improved, we got some shear stress, but look what we got. We got something that gives us a shear stress, let's call it tau, which is not function of z. It means it doesn't vary as I go from top of the beam to bottom of the beam. It's not function of z. Um, so phi is this is function of x. This is function of x. So uh, therefore this is a constant. So in Timoshenko, the shear stress does not vary along z direction. In fact, it is a constant shear. What it means that if I want to draw this, maybe if I can draw it here, therefore maybe I pick up another color here. So it has some value here, and then it goes down to a constant. So if I just magnitude, so maybe I draw this way. So everywhere you have the same shear. This is obviously a big problem. It's still a big problem. Improved compared to Euler-Bernoulli, but a big problem. Because we know that on the top, at the bottom surfaces, we don't have shear in general in a beam. So the shear is actually a parabolic profile, which is zero at the top, zero at the bottom, and it has a second order. This is a constant along the z direction. So Timoshenko beam theory still benefits from the one-dimensional simplified uh, version of beam calculation. It recovers the shear stress, but it recovers it in the wrong way, or the result is the wrong way, because it says that it will be a constant shear along the cross section, whereas we know that it is not constant. It cannot be constant, top and bottom, and there should be some second order variation. Now, in order to recover that, uh, there is a K factor, a famous K factor. Timoshenko K factor. So this K factor comes and gets multiplied by the shear stress. Let's say uh, when I calculate the shear stress, then we multiply this K factor, and K factor depends on the shape of the cross section, and brings back that compatibility of the shear stress that I just described here. So for example, just to note here, for a rectangular cross section of the beam, K becomes, according to James, or according to a table uh, in the James and Dime book, 12 plus 11 mu. So you can get this K factor from different references, and for I-beam is more complex, for for example, semicircle, and then you can get this K factor which multiplies to the stress, shear stress, that is. So kind of gives you the full treatment. So it's a fudge factor, if you like, to overcome this deficiency. Now, if you write the equilibrium equation based on this, so one thing again here is that we don't have any kinetic inconsistency, because we get some shear stress, shear strain and shear stress, contrary to Euler Bernoulli. And if you write the um, equilibrium equation, you will get EI V4W dx4, for example, is equal to Q minus EI K G A D2 Q dx2. This is due to shear. Deformation, that, because this is the fudge factor that I described. This is the shear modulus of elasticity. This is the cross section, and we know the rest of this. This is load. I don't mean to go through this heavily here, but just wanted to point out the major assumptions. Still, I have to do the sign convention, and the sign convention, I refer you to the previous table that we had. This table, this applies here also for Timoshenko beam. Depends on uh, which side of the beam you are, and then the phi is sign is here, and then you can take it from there, and the slope, which is dw here. So here, when I say w prime, I mean dw dx. Okay, so that should do the job for Timoshenko, I hope. And in the Next video, I will go to discuss the Reddy's beam theory, which takes care of this result that we have here, that the shear stress is constant at the section, and then we get our parabolic back. Thank you.